So for the main event tonight, we have a talk from Dr. Marianne Heida, who will tell us about how to actually observe black holes using all the equipment that we have here at Caltech and also elsewhere. Marianne received her PhD from the Netherlands Institute for Space Research in 2015. She's originally from the Netherlands. And she came here in 2016 to work with Fiona Harrison Group here at Caltech on X-ray satellite called New Star. And she works on follow up those observations with optical and near-infrared telescopes here on Earth. Sadly, she is leaving us next week to go back to her home continent of Europe, and I'm sure she will miss our nice weather very much. But yes, for the time being, let's welcome our speaker.
Okay. Thanks. So I just want to make sure, is the microphone working? Can people hear me in the back? Awesome. Okay. Right, welcome. So I'm going to use this next half hour to give you a brief introduction to black holes. And because, as Gao said, I am what is called an observational astronomer, which means that I use actual telescopes, in my case, telescopes that record optical and infrared light, to look at stuff in the universe. So this is me at the Palomar telescope, for example. So this is going to be an observer's take on black holes, which is different from, for example, a theorist's take on black holes. So what are we going to talk about? I will start with quickly explaining what a black hole actually looks like. What do we even mean when we say we're observing black holes? After that, I will explain how we usually find black holes, what we want to measure once we have found them, and last but not least, why do we even care about these things at all? This also means there's a bunch of things that I'm not going to talk about, so to prevent any disappointment, I am not going to mention information paradoxes, firewalls, or Hawking radiation. And unfortunately, I won't have the time to talk about gravitational waves either, but I'm sure there will be another talk about those sometime during the year. Okay, so let's get started. What does a black hole actually look like? Yeah, this is a little too... It's too easy, right? Too easy. But the essence of a black hole is obviously that it's black. It is an object in space that is so dense that when you get too close, even light cannot escape. So if you look at the black hole itself that is just sitting there in space all alone, it's black. No light can escape that can reach our telescopes, so we cannot see it. Now, fortunately for us, a lot of black holes aren't just sitting by themselves in space. There is stuff around them, stuff that is falling into them. And black holes that like that are like feeding on matter, as we call it. We call them active black holes. And those are usually the ones that we can observe. So this talk is really about active black holes. What do active black holes look like? Well, some of you may have seen this picture before. It was released earlier this year by the Event Horizon Telescope. And this was the first time that we got a really, really, really close-up picture of what a black hole looks like. And here in the center of this ring is a black spot that is what's called the shadow of the event horizon. So that's the bit where the light cannot escape anymore. And this ring of light is radio light that is emitted right before it falls in. So this is light that's coming from stuff that is falling into the black hole but isn't quite there yet. So the light can still escape. And this is sort of the last light that can still get out of the system and make it to our telescopes. Okay, so if we zoom out a little bit, what are we actually looking at here? So now we are moving away from observations and back to artist impressions because we cannot actually make pictures this nice. But there is a lot of information in this picture that we gathered through lots and lots of observations. So let's go through. Here in the middle is the black hole. Obviously, it's black. So the event horizon picture is sort of coming from this sort of dark ring here. Outside that ring, the most obvious thing that you see in this picture is this disk of gas. And this disk, the stuff in the disk is moving around the black hole and at the same time slowly moving towards the black hole. And eventually, when it reaches the inner edge of the disk, it will fall into the black hole itself. The other thing that's very obvious is this bluish jet that's coming out. So this is material that's moving away from the black hole. Notice that it's not coming out of the black hole itself. It starts a little bit above it. We're not entirely sure how close it is. It's pretty close, but we're not 100% sure yet. But it's definitely not coming from inside the black hole itself. But this is stuff that is moving at nearly the speed of light, and it's probably launched by magnetic fields that are threading this disk. And then the third thing in this picture is this big blob here on the side of dust. This is sort of a ring or a donut, if you will, of dust that is sitting outside the disk. And the main thing that we notice about this is that if we look at these black holes from the side, then this ring of dust will actually block our view of the black hole in the center. Okay, so the black holes that we observe, they sort of fall into two groups based on mass. So this is an example of what we call a supermassive black hole. These are the most massive black holes. They've got masses starting around a couple million, going up to several billions times the mass of our sun. And you really find them in the center of pretty much every self-respecting galaxy. Our Milky Way has one too, but it's not active. But there is a big black hole in there, which I will show later. The other group of black holes are much smaller, but they look very similar. They actually behave much the same way. So again, the black hole is there in the center. There is a disk, again. There is this jet, again. The main difference is that the material in this disk is all provided by this single star that is a companion star to the black hole that's a little too close and is very slowly getting stripped and feeding this black hole. But apart from the scale, this entire system would fit within the orbit of Mercury if you put the black hole at the center of the sun, whereas these supermassive black holes, if you put the black hole at the center of the sun, the event horizon would be somewhere beyond Pluto. Aside from the scale, they really behave in pretty much the same way. So these are what we call stellar mass black holes. They have a mass of a couple to maybe 100 times the mass of our sun. They are the leftovers of the most massive stars in our galaxy. And we think there's at least a couple million of them in our own Milky Way. But we only see them, again, when they're active. So when they have a nearby star, not all of them have such a star nearby. So we've only seen less than 100 of them out of the millions we think are out there. Okay, so we've got supermassive black holes and stellar mass black holes. Now, astronomers love to abbreviate things because nobody wants to write out supermassive black hole all the time. Unfortunately, these abbreviations are the same. So the solution here is to capitalize the big black holes and not the small ones. Okay, so I won't actually be using these abbreviations in this talk, but anytime I'm talking about the supermassive black holes, I will show you this picture, and when I'm talking about the stellar mass black holes, I will show this picture. Okay, so we know what a black hole looks like. It has a disk, it has jets. How do we find them? Well, it turns out active black holes are really, really bright. And to understand that, we can take a look at how efficient we can get energy out of matter. So say you have a pound of stuff, doesn't matter what kind of stuff, and you want to turn it into energy, so radiation in this case. Now, the most you can get out is what we call the rest mass energy, which is given by Einstein's E equals mc squared. So say your pound of stuff is 1/2 pound of matter and 1/2 pound of antimatter, and you combine them, you would get all the rest mass energy out. You would turn all the matter into radiation. So that would be 100% effective. If instead your pound of stuff is, say, oil or gas or coal or whatever is your favorite fossil fuel, and you decide to burn it, how much do you get out? Not very much. That's a lot of zeros. I'm not even going to count them. So this is only a tiny, tiny fraction of the rest mass energy that's coming out when you decide to burn your pound of stuff. Okay, so we can do better than that, right? What if we try nuclear fusion? It's what the sun does. It's what all the stars do to make energy. Must be pretty efficient. So you take a pound of hydrogen, you turn it into helium, you get about 1% of the rest mass energy out, which is still not that much, but a lot better, at least, than burning it in an engine. Okay, so last thing. Let's try to throw our pound of stuff into a black hole. Now we can actually get up to 10% of the rest mass energy out. So if you don't have any antimatter, this is actually the most efficient way in the universe of getting radiation out of your stuff, which is great. So black holes are really efficient at turning matter into energy. And that's why they're bright. And they actually emit this energy at lots of different wavelengths. So if we look at this system, for example, there is radio and infrared light where we can see these jets. There is this donor star, or this companion star in this case, that emits optical and infrared light, but that doesn't have anything to do with the black hole itself. And then this disk, that is the brightest thing about these black holes. It emits tons of optical light, UV and X-rays. And X-rays are actually a really efficient way of finding active black holes, because normal stars don't emit a lot of X-rays at all. They're not hot enough. So if you see a bright X-ray source in the sky, there's a good chance it's an active black hole. So let's have a look at this. If you want to know about all the different features of this black hole, so the jets and the star and the disk, you have to look at all these different wavelengths, and you have to use tons of different telescopes and people with expertise to study these things, which actually makes it a really interesting field. So here on the left, we've got the fairly long wavelength, low energy radio waves that we can see on the ground with these nice big dishes. Then here in the middle, we've got visible light, which is, well, in the middle as with regards to wavelength and energy. And we can see those also from the ground, obviously, with big telescopes, for example, like the Keck telescopes on Hawaii. And then if you want to see the UV and X-rays, which are much more energetic because they have much shorter wavelengths than visible light, unfortunately, those do not penetrate the atmosphere. Or maybe fortunately, actually. But unfortunately, if you're an X-ray astronomer. So you have to go into space, launch a satellite, and get above the atmosphere to actually see the X-rays. And we do all of these things. But if you want to find the black holes, it's best to start with those X-rays. Okay, so this is a picture of the night sky. Not from LA, obviously, but anyways. You can see here, this is invisible light. So there you see the disk of the Milky Way. We are sort of on the edge of the Milky Way pancake. So if you look towards the center, you see this flat line. Here's the center of the Milky Way. You see all this dust that is blocking our view at visible light. And you see all these single stars, right? So if you look at the same thing but in X-rays, it looks very different. First of all, the resolution is a lot worse because it's actually really hard to focus X-rays. Second, you still see this disk structure, but you don't see the dust because the X-rays go straight through, which is very convenient. And third of all, there's a lot fewer sources. So all these single sources are very energetic, and most of them are actually active black holes or neutron stars in our Milky Way that are actively eating stuff from their surroundings. So this is a great way to find black holes. And the fun thing is that many of these active black holes, they're only bright in X-rays for a while. So they become really bright, they stay bright for a couple weeks, maybe months, and then they fade away again. And then a new black hole will pop up somewhere else. So we've got telescopes keeping an eye on the X-ray sky at all times. And every year we find a couple new X-ray sources and a couple new black holes, which makes this a really interesting field. Okay, so this is how we find stellar mass black holes. Supermassive black holes are not that hard to find because you know that they will be in the center of their galaxy because they are so massive they can't really be anywhere else. So all you have to do is point your telescope at a galaxy, and you will notice if it has an active black hole. So this, for example, is a galaxy called Centaurus A. So this is not our Milky Way. This is a different galaxy. It's not too far away, though. And you see it has the same nice dust lanes as our Milky Way does. But this one in the center has this really, really bright optical source. And if you point a radio telescope at it, you will notice that there is a bright source in the middle, and it's got these huge jets and blobs of radio light. And then in X-rays, it looks even crazier. So if you combine all these observations, you will see that these radio and X-ray blobs are bigger than the galaxy itself. That is, all that energy is coming out of the supermassive black hole in the center because it's eating stuff and spitting out these huge jets. So you notice this this supermassive black hole is actually putting out about the same amount of energy or even more as all the stars together in that galaxy. Okay. So supermassive black holes, if they're active, they're not hard to find. If you go a little bit further away, then you don't get these nice resolved X-ray images. You won't see these jets, but you will see a lot of points. So this is the X-ray equivalent of the Hubble Ultra Deep Field. This is what's called the Chandra Deep Field South. That is 80 days worth of staring at a spot on the sky with the most sensitive X-ray telescope that's up there. And maybe some of you have seen the Hubble Ultra Deep Field. It's like basically they took the Hubble Space Telescope, they pointed at what looks like a blank spot in the sky, stared for a really, really, really long time, and then you see all these galaxies popping up. This is similar, except here every dot is an active supermassive black hole, which is pretty awesome. There's about 5,000 of them here, and this picture is about the size of the full moon. So there's a lot of these sources out there. Yeah, you can count them, but I haven't. Okay, so you've found your black hole. You have used your X-ray telescope. You have found a nice X-ray source. You've figured out that it's a black hole. What are we going to do next? We want to measure something, right? Because that's what scientists do. We measure stuff. So what do we want to measure about a black hole? Well, black holes are really simple, actually. They only have 3 properties, which is way less than most other things in the sky. They have a mass, which also sets their size, but those things are related. They have what we call a spin, which means it's basically tells you how fast it's spinning. And then in theory, they can have an electric charge, but in practice, for astrophysical black holes, the charge is 0, which makes things really easy because we only have 2 things that we have to go after, a mass and a spin. How hard can this be, right? Okay, well, so to measure the mass of a black hole, you can't use the X-rays anymore. You have to look at something that is going around the black hole. And basically, we use Kepler's laws, which are the same laws that tell you how planets move in the solar system, to figure out how massive this black hole is. And in the case of stellar mass black holes, there is an obvious candidate because there is this companion star that is sitting pretty close to the black hole and it's going around it. So we have our what we call test particle. And all we have to do now is figure out how long the period is, so how long it takes the star to go around the black hole, and how fast it is moving. So how do we do that? Well, we stare at this star with an optical or infrared telescope, and we measure how fast it's going. And we do this at several points in the orbit. So these are very small systems, so we can't actually see the star move on the sky. So we don't see this movement at all because it's just a single point. It's much too small. We cannot resolve it. What we can see is how fast the star is moving away from us and towards us. So in this picture, there's the black hole. This here is the companion star, and here is the observer, so us. And if the star is in this bit of the orbit, it's moving away from us, and we can measure that. And if it's in this part of the orbit, it's moving towards us. And so by measuring the velocity away from us and towards us at many points, we can make a nice sinusoidal curve like this, and that will give us the period and the velocity. So how do we measure velocities? We use what's called the Doppler shift. Maybe you've heard of this. You've probably seen, or heard rather, this effect whenever an ambulance or a fire engine drives by, and when it's coming towards you, you will hear the sound being rather high, and then when it passes you, the pitch changes, and it suddenly becomes a lot lower. The same thing happens with light, actually. So we look at the spectrum of a star, which means that we are unraveling all the visible light into their different wavelengths, so you get sort of this rainbow type. And stars have sort of what we call absorption lines at very specific wavelengths where a certain element, for example, hydrogen, in the atmosphere of the star is absorbing the light. So this happens at very specific wavelengths, and we know these wavelengths because we can measure them on Earth. So we know, for example, that if a star is not moving, we will expect these black bands, these absorption lines, to be over there and over there and over there. Then when the star is moving towards us, this light gets a little bit blue shifted, and the absorption line moves. And when it's moving away from us, it moves in the other direction. So by measuring the position of these dark bands, of these absorption lines, we can figure out how fast the star is moving. And by doing that multiple times, we get this nice curve, and we measure the period and the amplitude. And then we need to know a couple other things, actually, but that's kind of complicated, so I will skip over that now. But this will give us an idea of the mass of the black hole. Okay. So this works for stellar mass black holes. There is only one supermassive black hole where we can do something similar, actually even better, and that is the supermassive black hole at the center of our Milky Way. And this is just an awesome picture. We are starting at Earth, and we are zooming in to the center of our galaxy. just to show you how amazing these observations are. These are all observations. So we are now passing through the dust. We're switching to infrared light because that passes through the dust a little bit better. And we keep zooming in and zooming in and zooming in. And people have been doing these observations since the 1990s. So we have almost 30 years, oh gosh, worth of observations of this tiny little patch of the sky. We're getting there. Still zooming in. There we go. So, you can see a couple stars here, and that actually is the location of our supermassive black hole, which you see is sort of kind of pulsing. I actually have a better video of the stars themselves. So these are all the stars in the very, very center of our Milky Way, and you can see they are going around something. This star in particular, we have seen it make an entire orbit, so there it goes. So all these stars are moving around something that's sitting right there. It's about 3.5 million times the mass of our sun, and no light is coming from there. So no matter what you try to put there, 3.5 million tiny stars or whatever, you would see some light coming from it. So this was, until we got the picture of the black hole earlier this year, this has been the strongest evidence that supermassive black holes actually exist for a long, long time. And this is amazing. This is an incredible movie. We actually have a full 3D view of what all these stars are doing, which gives us the best measurement of any black hole mass anywhere. So this only works in our own Milky Way. For supermassive black holes in other galaxies, we use sort of the same idea, but we can't see individual stars, so we look at the movement of all the stars combined, or of gas in the center of these galaxies. But always the point is that we use the motion of things, stars or gas, around a black hole to measure its mass. So that's masses. Now we get to spins. Spins are tricky. So to measure the spin of a black hole, we usually use the X-ray spectrum. So it's the same idea. We take the light and we unravel it in all its different wavelengths, except we don't use visible light here. We use the X-rays. And X-ray spectra of black holes have this. These are a little bit sort of simplified. But the point is that there is this one big peak, this big feature that is due to iron in the disk. And then there is this pretty tricky general relativity bit that tells you that if a black hole is rotating, the disk can extend out to a certain distance from the black hole, and which is outside the horizon. But if you get closer in, then the particles cannot go in circles anymore. They will just fall straight in. So this disk ends somewhere outside of the black hole, and the location where this disk ends is given by general relativity. And if you have a spinning black hole, if the black hole is spinning in the opposite direction of the disk, then this location where the disk ends gets moved further out, and if the black hole is spinning in the same direction as the disk, gets moved further in. And what you see then is that the shape of this line changes, because if you get closer to the black hole, then the effects of general relativity get stronger, and they distort the shape of this line. So the line basically it gets wider and a little bit lower. So by measuring the shape of this line, you can get an idea of where the inner edge of the disk is, and that then tells you something about the spin of the black hole. Not everybody believes this method. There is another method that usually disagrees with this one, that is even less trustworthy. So we've really only have spin measurements that anybody sort of believes for maybe a handful, like 5 or 6 stellar mass black holes. And for supermassive black holes, I don't think anybody has really done a measurement that anybody else actually trusts. So this is really hard, but we'll get there eventually. Okay, so we've measured the spin and the mass of our black holes, assuming. Why do we care? Well, there's lots of reasons to care, actually. Black holes are cool. That's reason number one. There is the physicist's reason. We want to figure out where general relativity is wrong. Where does it break down? How can we, at some point, mesh general relativity with quantum mechanics, and looking at black holes is actually great in that case, because black holes are the most extreme gravitational objects in the universe. So if general relativity is going to be wrong anywhere, it's got to be there. Of course, there's a lot of very nasty astrophysics in a way that you have to understand first before you can get to the general relativity. But this is the physicist's reason, I think, to look at black holes. If you're not a physicist and you don't care at all about general relativity, which is possible, there are still plenty of reasons to study black holes. So this is the reason, for me at least, to study stellar mass black holes. This is a plot, it's kind of busy, but I will walk you through it, that shows the evolution of stars of different masses. So here at the bottom of this slide are the low mass stars. Here's our sun. Here are stars that are even less massive than the sun. And these low mass stars are, well, I'm sure they are interesting for many reasons, but they are kind of boring in the sense that they will just end their lives as a white dwarf, and they don't really do much. It gets interesting when you get to the more massive stars. So here are stars that are about 8 times the mass of the sun, and then you go up, they get more massive. These stars will have a supernova explosion and leave behind either a neutron star or a black hole. If you get even more massive, these stars won't even go through a supernova explosion, they just collapse, or at least we think they do. And these massive stars are really, really important for you, although you may not know, because this is where all the elements that are not hydrogen and helium are made in the universe and dispersed. So stars fuse hydrogen into helium, and then helium onwards into carbon and oxygen and nitrogen, and all these very useful elements that make up our Earth and our bodies and our air and everything. And less massive stars do this too, but then that stuff just gets stuck into the white dwarf and it never gets out, so nobody else gets to see them ever. But these supernova explosions, they actually disperse all this stuff into the universe, where it can form the next generation of stars and planets and people. So these massive stars are really, really important for life and the universe and everything. So by studying these black holes that they leave behind, we can come to understand a bit more about how supernova explosions work and how these massive stars evolve. Because there are really, we sort of know the general picture, but there are a lot of details that we don't understand yet. And in fact, just how to make a supernova actually explode, we don't really know. So studying the black holes that they leave behind is a good way to figure out what the hell is going on. Okay, so supermassive black holes kind of have a different take here. So supermassive black holes are found in the center of every galaxy, as I told you. And there is this weird relation between the mass of the supermassive black hole, here on the y-axis, and the mass of one of the parts of the galaxy called the bulge, which is this blob of yellow stars. So they don't really relate to the spiral arms. They only relate to this yellow, puffed up, sort of elliptical bulge. And it's not really clear why. There is no obvious reason why the supermassive black holes should know about all these stars, because they don't really interact with each other. And vice versa, these stars shouldn't know about the black hole, because the black hole only really affects the inner, maybe a couple thousand of stars, but all the billions of stars out there, they don't care if there's a black hole in the center, because its mass is only a tiny fraction of the total mass of this galaxy. So it's not super obvious why there should be a relation like this, and we think it must have something to do with the way these black holes form, the way the galaxies evolve and grow in the early universe. And if we can figure out what's going on here, this will teach us a lot about the early days of the universe and how everything that we see today actually got here. These are only 2 tiny questions. Well, okay, 2 big questions, but there's lots of other big questions. So we don't know how supermassive black holes form. We don't understand how they grow so fast in the early universe. We see supermassive black holes that are billions of times the mass of our sun after only, when the universe was only a couple million years old, and we don't understand how they got there and how they grew so fast. How massive can a stellar mass black hole be? The most massive ones that we had seen were about 20 solar masses, and now LIGO is finding all these 50, 60 solar mass black holes. Where are they? Where did they come from? What is the upper limit? We don't know. Where are the intermediate mass black holes? We see these stellar mass black holes, and then there's a huge gap, and then there's these supermassive black holes. There should be something in between. We think there must be something in between. We haven't seen it. We have no clue where they are. So there's lots of open questions. If anybody wants to go into black hole research, we are not done yet. But I think I am done for tonight, actually. So I will answer any questions that you have now. Thanks.
All right, thank you. Is it working? Hello?
Yes.
All right, thank you very much, Marianne. Any questions?
Oh, here, you do this?
Oh, you do it.
Okay. Yeah.
Oh, hold on.
Wait.
Let me give you the microphone.
So I have two quick questions. So first of all, why is the spin related to, I guess, the size of that central disk?
Okay. I am going to say this has something to do with general relativity.
Okay.
Sorry. There are a lot of details there that I honestly don't know because I don't work on this particular problem. But it has to do with how fast the space-time is like the black hole is rotating and it sort of drags space-time with it, and then where this final orbit is where particles can go around in a stable circular orbit, it's called, that changes depending on how fast you move your space-time.
Okay, yeah, that was really helpful. And then also, how do black holes tell us about the supernova that came before? Because, I mean, the black holes are just kind of...
Good question. So if you can measure the mass of the black hole of the black hole, especially if you know what kind of star it came from, so it would be very helpful to be able to measure both of them. Then you know how much mass is lost in the supernova explosions, because and that tells you something about how the explosion works, how it launches this entire envelope into space, how much of this envelope then falls back. There's a lot of details there that can tell you something about what is actually happening. And especially, so we think that there should be this sort of gap, like up to a certain mass, a star will have a supernova explosion when it dies and leave behind a fairly small black hole, because a lot of the mass is lost in the universe. And then at some point, they don't have the supernova explosion anymore, they just collapse. So we think that there must be a hole somewhere in the distribution of black hole masses. Like you find black hole masses up to a certain limit where they have supernovae, and then there is a gap, and then above that you find black holes that just collapse in one go. We haven't really figured that out yet at all, but that is really going to tell us something.
Thank you.
Yeah.
You mentioned in the middle of the Milky Way there's an inactive black hole. What's
Yes.
the difference between active and inactive?
Most of the pictures, like this big artist impression I showed with this disk and these jets, those are active black holes that are actually feeding. Like matter is falling into them at a fairly high rate and turning into energy, and they are very bright at all wavelengths. The black hole at the center of our Milky Way isn't really doing very much because, well, I'm not entirely sure why actually, but not that much stuff is falling into it. So it's what we call quiet. So it's not so bright. It doesn't have these huge jets. I mean, sometimes every now and then it blips, it does something, but it's much, much fainter than the actual active black holes that we see in other galaxies. So it just means it's just not doing much. Yeah.
Thank you.
We have a question from another room.
Oh, boy.
Yeah, so we have a question from the overflow room, which is, what is the typical spin rate of a black hole?
So this is funny. We're not very good at measuring them yet. So mostly what you can say is it's not spinning much or it's spinning really fast. So a bunch of them appear to be spinning really fast. There is a maximum spin rate for a black hole, which is given by something with the speed of light at the event horizon. And some of the black holes that we measure seem to be spinning like close to maximum. Then again, LIGO keeps finding these merging black holes that don't seem to be spinning much at all. So this is actually a bit of a problem. We don't really know how to reconcile those things. Yeah. But let's go there. Oh, sorry.
I don't do anything in astronomy or anything, but I do read the newspaper, and I remember a couple months ago there was the article that came out saying that someone had taken a picture of the black hole, and I think it was a woman, and so everyone was like, yay, women in science. And my question was she just like sitting one day and happened to like take a good picture, or how did she, and wasn't she a postdoc? She was also like in training or something. Can you give a little background behind that? Because it seemed like something that was a really great thing to happen.
So the background, as far as I know it, is this woman, Katie Bauman. She was a grad student in she was a member or leading of one of the groups that were trying to make the picture of the black hole. So that radio light is pretty tricky, and what they were doing was even trickier than that. So they needed to combine the observations of a lot of different telescopes all over the world. So they would have the largest possible. They were basically turning the entire Earth into a very large telescope and only observing on very small patches of it. But then that's how they get the high resolution. So they had observations from Antarctica and Hawaii and Chile and everywhere, and they had to ship all that. They got tons and tons of data. They had to physically ship all that stuff, because it's too much to do it over the internet. If you want to ship stuff from Antarctica, you only have a couple months a year. Anyway, it was very complicated. And then they had to write all the software to turn all this data into a nice picture. And they didn't want to rely on just one package. So there were several teams that were all developing their own software to turn all this data into this picture. And Katie Bauman, who is actually, I think, an incoming assistant professor here at Caltech in this spring. I think she will give one of the talks, actually, later this year. So you can ask her. But she was a member of one of these teams. And so it's very much a team effort, especially a big project like that. Like the Event Horizon Telescope, actually, they won the Breakthrough Prize in Physics like yesterday or something. So they got, $3 million? They had to split it among, I don't know how many 100 people, because everybody did something, right? You need all these contributions. So you can't say, she made the picture. It was very much a group effort, and that is what Katie herself has been emphasizing all the time. It's like, it's not just me, it's all of us. So I hope that gives some sort of background.
All right, with the interest of time, let's do one last question. But then Marianne will stick around.
I'll hang around for a bit, yeah. Do you want to do one in the back?
Really good.
There's a boy in a red t-shirt who really wants to ask a question.
So if the event horizon prevents even light from escaping, how are we able to see such a bright light coming from the vicinity around a black hole?
Right. So that's because that light is coming from just outside the event horizon. So it just, once you're inside, light cannot get out anymore. But as long as it's outside, it can still escape.
Thank you.
So there is no light, there is nothing coming from inside the black hole. Anything you see in these pictures is coming from outside the event horizon. It can come from very close to the event horizon, but it's always going to come from outside of the event horizon. Okay.
All right, let's thank Marianne again. All right, so all hot questions that you would like to ask, everything except the controversy about TMT, we are not going to talk about that. So, if you don't know what that is, great.
So, no, it's okay. Thank you.
Because we are recording, so we would like to have them. Excuse me.
So this is a question about the image of the black hole. So this using radio telescopes and looking, basically, you're seeing a silhouette of the black hole, right? So the perspective of the observer is Earth looking at that image. So would that image of the silhouette of the black hole be the same if you were looking at it from any other perspective?
So the question, would it be the same if you're looking at any other's perspective? In the exact details, no. However, it'll look pretty similar, I'd say. Really what you're seeing in the silhouette is you're seeing the light that happened to be from the hot material that's outside of the black hole sort of being gravitationally lensed or sort of bent around the black hole itself, right? And so I imagine that the actual how it would look from other perspectives just depends on what material happens to be on the other side of the black hole from that perspective. But also you have to keep in mind that this particular image is not actually 100% like what the black hole would look like in that light as well. It's sort of like the best reconstruction that you can make given the data that the Event Horizon Telescope observed. So the Event Horizon Telescope is essentially taking very, very small, sparse sampling of the actual data that's out there. So if you're a little bit more familiar with technical things, it's sort of taking little points in the two-dimensional Fourier transform of the sky brightness. So if that if that means nothing to you, don't worry about it. Basically, imagine you have a giant radio dish that's like the size of Earth, except instead of having the entire dish, you just took a little hole punch and punched 10 telescopes out of there, right? And the rest of the dish is gone. All you have is the little holes you punched. That's basically taking that little telescope and trying to reconstruct the kind of image that you would get from the entire Earth-sized telescope, right? And you can imagine that's actually really, really hard to do. And so there's a lot of work that was done in making sure that you can actually recover, a reasonable image. And people tried many different methods, and they all sort of converged at roughly the same answer. And that roughly the same answer is the picture that you saw.
Right, I have a question. Who are you? I forgot to introduce everyone, sorry. So please introduce
Great
yourself.
question. Hi, my name is Dylan. I am a third year, soon to be fourth year grad student at Caltech. Who are you?
I already introduced myself in the very beginning.
You did? Well, let's repeat it for the audience here.
My name is Gao Tinyanon. I'm a soon to be fifth year graduate student at Caltech.
My name is Mia Delis Reyes. I'm a second year, soon to be third year grad student here at Caltech.
My name is Janosch. I just finished my PhD at the University of Cambridge.
Hi, I'm a community college student, and I'm getting ready to transfer next year. And I'll soon be taking the GRE. I was wondering if you have any studying tips or anything you could give me so I could try and survive the GRE and the subject GRE for the physics part.
All right, well, I think we are all in agreement here when we say that both the general and the physics GRE are not good tests of your ability as a researcher. Everyone knows that, including the graduate admissions committee. So I think this is true at pretty much any institution. They all know it's a bad test, and they, in some cases, will make you take it anyway, unfortunately. So the answer is do your best, but honestly don't worry too much about the score, because I think Dylan probably knows this the best because he was on an admissions committee, but I'm pretty sure they don't put that much weight on the scores. A lot of the best programs, like here at Caltech, we don't put that much weight on scores. And the physics GRE is no longer a required component of the application. So, sorry, that was not really good advice. I can give you more study tips later, but I... Oh, yeah, more questions? Great.
Hi, this is for Janos. Just wondering where fluid dynamics, accretion disks, and magnetic fields meet.
Well, so fluid dynamics and magnetic fields are pretty much the main way to model accretion disks. So accretion disks are composed, at least accretion disks around the stellar mass black holes, like Marianne was talking about, are composed mainly of highly ionized gases. So these are, so that means you have electrons knocked off of your hydrogen, and that means they can be conducting, so they have magnetic fields tied into the fluid. These magnetic fields are actually really important for this process of slowly moving material in towards the black hole that she was talking about. Does that answer your question?
Absolutely. Thank you.
Hi. I have degrees in art, so I have no idea what I'm talking about. But I've always wondered, they talk about the galaxy is expanding. And as it's expanding, what's outside there that lets it expand? I mean, what is it expanding into? And where are we going with that? Or do we hit an edge and then it implodes again?
Okay, so when we talk about... Hello, is it on now? Okay, all right. When we talk about things expanding, we don't usually talk about a single galaxy. We're talking about the entire universe. Yeah, the entire universe, right. I guess the best sort of imperfect analogy that I can think of is this sort of classic analogy of raisin bread. So if you have a bunch of raisins in like some dough and then you bake the dough, the bread expands. And as it expands, the raisins move apart from each other. And so the question is like, what is it expanding into? There's another imperfect analogy to answer that, which is if you draw a bunch of dots on a balloon and then you blow it up and you imagine living like on the surface of that balloon. The balloon is not really expanding into anything. Like the surface of the balloon is not really expanding into anything. Does that kind of make sense? Yeah, it's just that the space itself is stretching. What's going to happen in the future? We don't know. This is what a lot of theorists argue about. There are, like as you mentioned, there are some theories that talk about sort of a cyclic cosmology where, you know, eventually our universe stops expanding and begins collapsing in on itself, and then maybe this happens a lot, I don't know. The problem is that a lot of these hypotheses are not really testable. And so past some certain point, you have to sort of just throw up your hands and be like, well, I don't know, if it's not testable, like is it still, you know, what we traditionally call science? Can we do anything about that? And in some cases, maybe. Like people have made arguments that maybe you can see like the imprint of this kind of cyclic expansion and collapsing on, you know, certain signatures in the sky, but the data are really just not good enough to tell, and it's really kind of fuzzy, I think. So there's a lot of controversy over when people make claims that they can understand what's going on in the really, really grand scheme of things. I hope that answers your question. I know it's not very satisfying, but much of cosmology is not satisfying. Yeah. Yeah, sounds good.
Oh, so it's not so that we can hear it. It's so that the people on YouTube can hear it afterwards.
So you can hear me now, right? Awesome. So I read somewhere that the universe expanded very quickly after the Big Bang, and then it slowed down, and then it accelerated again. Do you guys know what the most credible theory is for that variation in speed? Or your opinions, whatever.
Yeah, so the theory that you're referring to is called inflation. And inflation is sort of something that, again, nobody really understands, but people think is important and necessary to explain, in particular, why the universe is so homogeneous, so pretty much the same on large scales. Right? And we know the universe is pretty much the same on large scales in several different ways. One is if you look at microwaves coming in from the very, very early parts of the universe. This is called the cosmic microwave background. Pretty much like it looks almost exactly the same in any direction. The variation between one direction and another direction is like 1 part in like a million or something like that. And so how do you get the entire universe to sort of look the same in all directions when it's such a gigantic thing, and it can't even, like, different parts of the universe can't even talk to each other because they're so far apart that light would take longer than the age of the universe to cross that distance. Right? Information can't travel faster than the speed of light. And so the idea is that, and also how do you get these fluctuations in the beginning? And the idea that various cosmologists have put forward is that in early times, the universe was extremely tiny. And when you're extremely tiny, you get really random fluctuations due to quantum mechanics. And that's sort of what gave the initial seeds of structure. And then that structure sort of had to blow up to really large scales. And so you have inflation to get that as well. And then past inflation, you start being dominated by various other forms of energy. So I'm going to forget like all the different but at some point I think the universe was radiation dominated by the energy density of light, and then at some point it was matter dominated, so dominated by the force of gravity, and in this era we're actually dominated by dark energy. And so sort of relating back to the question you asked earlier, what's going to happen in the far future, a lot of astronomers think that because the universe is currently dominated by dark energy, and dark energy is actually making the universe not only expand but accelerate in its expanding, they think it's just going to keep accelerating forever. Astronomers love extrapolating to the future and saying, what's happening now, it's always going to happen. And so essentially that's sort of like the big rip theory, right? And they think at some point everything's just going to fly apart, and the universe is going to become a cold, dead place. So on that note, we'll take the next question. On that very cheerful note.
What do you do with galactic archaeology, and does that relate to astrobiology?
Okay, unfortunately it is not actually related to astrobiology, sorry. I realize now that it sounds super cool, but it's actually a lot less cool than that. Okay, so galactic archaeology. So in archaeology, the idea is that we learn about the past by seeing what previous cultures and civilizations and people left behind, right? So you find like a shard of pottery on the ground, and then, I don't know, I hear that archaeologists like to lick things. So you maybe like lick it, or you like test it. I don't know, use mass spectrometry or something. I don't know what archaeologists actually do, I'm sorry. And you can figure out, you can date it. You can like figure out how old it is and what it's made of, and like maybe something about the people who used this shard of pottery in the past, right? So unfortunately, you cannot lick a star. You cannot perform mass spectrometry on a star. And so we do apply basically the same concept. We figure out which stars are the old stars, and what do they have in them, and what does that say about the any galaxy at that point in the past. Does that kind of make sense? So I measure something called manganese. I measure the element manganese, and this is because manganese is a really good tracer of this particular kind of supernova called the type 1a supernova, which is a little different from the supernovae Marianne was talking about. But the idea is that by measuring the amount of manganese that are in stars right now, we can figure out how much manganese was in the galaxy when those stars formed in the past. And so that sort of gives us a window back to the past, and we can figure out stuff about the supernovae that happened then. Yeah. I hope that made sense.
Janos, what are some of the questions or large questions that you're trying to answer in like the fluid dynamics in your field that you're trying to work on? And like, what are, say, the major difference between, say, if you're doing fluid dynamics, say, on Earth versus in the accretion disk or actual in space in general?
Yeah, so those are very good questions. To answer your first question, a large problem with accretion disks is that we really despite having come a long way in our theoretical understanding, we're still pretty far off from knowing exactly how they work. There is a standard model of accretion which says that you have some thin disk, and it's the turbulence in the disk acts like viscosity and moves stuff around. But there's a lot of simulations and observations of these systems that suggest that might not be right. So there's just the general theory of what's going on there. Specifically related to these low-mass black hole systems, like Marianne was saying, one of the really hard things to do there is to measure the spin of the black hole. Since all the light comes from the disk, one of the ways you might be able to measure this spin of the black hole is by looking at how exactly this disk works. So that's a major question I've focused a little bit on in my PhD. No. And so you asked also about the regimes on terrestrial fluid dynamics and astrophysical fluid and gas dynamics. One of the major differences is that a lot of fluid dynamics on Earth is modeling viscous flows. So you have some viscosity, like you think of honey, it has some viscosity. It's a very slow oozing fluid. The opposite is true in astrophysics. You have very diffuse, basically inviscid gases. You also have no viscosity.
So you mentioned trying to figure the viscosity in the accretion disk. Is that even, how much of that would that have an effect in such a diffuse gas?
Yeah,
such low pressures?
So I shouldn't have said viscosity. Back in the 70s, people tried to use a viscosity to model how these accretion disks work, just saying because they didn't have a better explanation for how the matter gets transported. What they're really appealing to is turbulent eddies within the flow. So these swirls of gas cause material to move inward. Sorry, does that answer your question? Sure. Yeah.
So would it be more like, I guess it would be more their own, like say plasma dynamics or something like that?
Yeah, that's plasma dynamics is even more diffuse, so it becomes a little harder because of that. One of the other big differences I mentioned earlier that magnetic fields are really important to this turbulence in the disk. And on Earth, you have very few magnetized fluids. There are some experiments looking at magnetized liquid metals, but they're very extreme case.
Thank you.
Yeah.
This is along the same lines. In terms of, you're doing computational work?
Some computation, some analytic work. Yeah.
So what's the size of your computational cell? I mean, you're dealing with discretizing this thing. It's got to be huge.
It's way too big, yeah.
And how big are your turbulent eddies then? And you must be doing some sort of turbulence modeling? Eddy viscosity or something?
So this magnetic turbulence in disks is known as, it's caused by people think it's caused by what's known as the magnetorotational instability. And there's a lot of argument about whether or not our simulations of MRI turbulence are actually resolved. And basically what people do is they increase the number of cells they have in their simulation and see if the bulk processes and the things they measure change. The real answer is we're probably not actually resolved, but the hope is that you can get at the large-scale processes happening in the disk, even if you can't model the very small-scale flow dynamics.
Okay.
Does that answer your question?
Oh, pretty much, yeah.
I'm having a little trouble understanding the geometry of the singularity of a black hole. Mainly I guess I'm looking to understand whether it's a three-dimensional event horizon or just some disk. As you speak about accretion disks, you make it sound like a two-dimensional thing.
I'll draw something, I guess.
Thank you.
The event horizon is a spherical thing. I'm talking about a lot of the models that have been made thus far are of very thin disks, because if you look at how rapidly the disk is rotating, then you'd expect centrifugal forces to be dominant, and you'd expect everything to flatten like a pancake. There's a lot of argument about how thin these disks actually are, but this essentially two-dimensional picture of a disk that I'm talking about is there's sort of two singularities here. There's this Schwarzschild radius, which measures the event horizon of the black hole, but then there's also this outer edge or inner edge of the disk. And Marianne mentioned that there's some. If you go into relativistic arguments, then there's some innermost stable circular orbit where if you have stuff interior to this, it'll just flow directly onto the black hole. So the standard picture is of a disk that's pretty thin, which extends up close to the black hole. And this you could think of as sort of a 2D matter horizon, not really an event horizon. But it is the event horizon itself is a spherical thing.
So to sort of summarize what Janos said in maybe a more analogy-oriented way, if you take a ball of pizza dough and you give it any sort of spin, it's going to flatten out, right? And that's why we see this disk of matter, even though the event horizon itself is spherical. Does that kind of make sense? So the event horizon itself is a 3D object. And actually, if it spins fast enough, we think it is probably more like a weird, flattish spherical object, like if you took a basketball and squished it a bit. But the disk itself, because it's rotating so quickly, really flattens out into what Janos describes as this really thin matter horizon disk thing.
Thank you.
Now, things go into the black hole. Are there different theories about what happens to the things that go into the black hole? And what are those theories?
So nobody really knows what happens to things after it falls into the black hole. And the reason is that in order to find out what happened to that thing, you'd have to get information out of the black hole. And information can't travel faster than the speed of light, but you have to travel faster than the speed of light to actually escape the black hole. That's not allowed by the laws of physics. So who knows? The theories that, like general relativity, that predict the observable properties of black holes do say things about the interiors, but it's unclear whether the theories actually apply in the interior because it's not testable.
Question for you guys. Based on the activity of the black hole, does that correlate to the speed of the disk or the speed of the black hole itself spinning?
So I think Marianne talked about being able to judge the inner edge of your disk based on this relativistic iron line. One of the reasons accretion disks are, especially around black holes, are so efficient at getting energy out is that the faster you go into the further you go in towards this close compact object, the faster the material's going to be moving. That's just, if you think about the motion of planets in our solar system, you have very similar relationships between angular velocity and distance from the sun. And that still applies, except that you're getting much, much closer to a black hole. And so the matter's rotating much, much more rapidly. And that, in turn, gives you a much hotter disk. So that gives it the really large temperatures and really bright disks that we see. Does that answer your question? Sorry.
So taking off on the geometry question of a black hole, so mass warps space-time, right? So if we think about, like, a mass in space creates a gravity well, right? So how do you kind of visualize in your own mind what space-time looks like from the perspective of a black hole. Like, is it in every direction there's a gravity well from a three-dimensional standpoint? Is that the right way to think of it? Or is there a better way to think of it?
Yeah, I would say yes. That is the way I would think about it. I mean, if you want a visual example, the film Interstellar, which, okay, I don't like the film Interstellar because I don't like Matthew McConaughey, but the film itself, the image that they show of a black hole is actually the best approximation that we have right now of what a black hole, a black hole in its full 3D glory would look like to us. So one of the Caltech physicists, Kip Thorne, actually worked on this film and was a consultant. And so we hope there is some scientific accuracy.
Yeah, well, also the gravity well picture that you're talking about, it's sort of like a visualization of potential energy as a function of position, right? And so it's not something that you would actually see, like, in real life. It's not, you never see, like, a little plane and then, like, here's a dip, right? It's just like, visualizing the energy. Yeah.
This is actually a question for you. So how do you do you like infrared astronomy better than observational astronomy? Because I want to go in observational astronomy, and I know you could probably see more in infrared. So what made you want to go into infrared instead of observational?
Yes. So I guess observational astronomy is a more encompassing term that it includes observations in the optical light and also in infrared light, or in radio or X-ray. So it covers everything. So in ideal world, if you're an observational astronomer, you should learn how to use all the tools that are available to you. And my advisor keeps, remind me this every day. But the problem is that in all these different wavelengths, the technique and the instruments that you use to detect these lights are very different. Optical and infrared, at least in the near infrared, are not very different. There are some subtle differences. The price being the biggest one, because optical detectors are in every single one of your phones or small pocket cameras, so it's a lot cheaper to make optical sensors than infrared. But infrared can also give you information that you can't get in the optical. One of the main things that Marianne also talked about is that if you have a lot of dust covering your source, an infrared light is much better at getting through dust than optical light. Another thing is that a lot of molecules, so if you look into stars or planets or nebulae in the optical, what you see are light that are emitted from atoms. So when you see like nebulae that look reddish or greenish, these are all colors that are coming from spectral lines from atoms. When you move into the infrared, you start to see spectral features from molecules, and you now get to learn not just carbon or oxygen, but you can learn about carbon monoxide, you can learn about methane. And these are very important in, say, atmosphere of planets that are not in the solar system.
First, just to comment on what you're saying. I think one of the reasons to be in infrared astronomy right now is the James Webb Telescope. When you look at the universe in a way that we haven't really looked at before, you're certain to find something unusual and unexpected. So I wish you well. What I was wanting to ask about is that the color values in that picture, you're using radio waves, so you've decided to pick different false colors to demonstrate what you have. And there's some things that are like a strong yellow, which gives the impression of being bright, and other things like this. Can you explain what the significance of the colors are? And also, is there a Doppler noticed between one side and the other to indicate maybe a direction of spin or something like that?
That's a great question. So first of all, to address the color map thing, essentially the color maps that people use are pretty much arbitrary, right? The data that you have basically just tells you how bright the light is, in a given pixel, right? It's a grayscale image basically. And if you talk to like old school radio astronomers, they all use like grayscale images, and they think that it's harder to trick the eye that way. Right? But color maps sort of bring out details so that you can really just like stretch your colors and play with them however you want. And you can sort of emphasize, for example, the brightest parts of your image, or you can bring out fainter details that may get washed out, right, if you sort of put everything on a linear scale. And so a lot of it is sort of just taking the same data that you have and visualizing it in different ways so that you can pick out different details they're all in the data, but you may not like easily see with your eye at first glance. And the second question was, is there Doppler information in this Event Horizon Telescope image? And the answer is yes and no. So every radio interferometer is measuring some chunk of light from one frequency to another frequency, or as optical infrared astronomers like to say, one wavelength to another wavelength. This is constantly a debate as to whether frequencies are better or wavelengths are better.
It's
definitely frequencies. And so basically, you're not just in optical telescopes, when you're taking an image, usually what you have is only one number, right? You have like all the light that happened to fall between wavelength 1 and wavelength 2. You add that all together, and that becomes your one pixel value. But in radio astronomy, what you actually have to do is you have to break that up into small chunks. So instead of just having wavelength 1 to wavelength 2, you have like wavelength 1 to wavelength 2, wavelength 2 to wavelength 3, right? Little chunks. And so yes, there is definitely information about how much light actually is at each frequency or wavelength. However, the Event Horizon Telescope is trying to make images that or take images of something that is so faint in such a short time that there's just so much noise in each given bin that you can't really trust the data, wavelength 1 to wavelength 2. You really have to just average it all up. And so that's what you're seeing in this image. Maybe later, if we build a whole bunch of more telescopes around the Earth and incorporate that into like the Event Horizon Telescope, then you'll be able to split up the different frequency chunks and try to get at rotation. But the other thing actually is these black holes, the time it actually takes for material to circle around the black hole itself is something like hours to days, right? And so you can imagine just taking a picture and then coming back like an hour later, taking another one, right? And doing that instead of just sort of averaging it all up. And you can actually probably see material moving around it. And I think the Event Horizon Telescope actually is planning to do these sorts of things.
So one cool thing I would add is that due to some, again, general relativistic effects, actually the side of the black hole that is brighter is the side that is coming towards you. And that's some weird things called Doppler beaming, and you can look that up. I'm not going to try to. Right.
Thank you. So I'm trying to have an understanding of how things are traveling into the black hole. So on one end of an extreme would be that they're going straight in. On the other end, it's kind of like a really tight screw where they're going in quickly. So I'm trying to understand the speed at which something is going into this black hole. And is it different if it's spinning really quickly? Is it going in there quicker, or is it if it's going straight, if it's going like a more linear path into the black hole? Is there a difference? And that idea came from the sort of this original thought of the fluid dynamics and the transfer of things in there. So, but Dylan also talked about that too, with regards to time. So trying to get a travel of things into the black hole.
Yeah, so one way I like to think about this is the scales in space are so gigantic that, you think a black hole is something that's really big, right? But compared to the scale that things are falling in on, the black hole is actually tiny. So imagine the black hole is like my fist here, and you're starting from some random position in this room, and you're trying to hit my fist. You're trying to fall into it, right? Chances are you're going to miss. You're not going to go exactly in the right direction and boom, straight in, right? Chances are you're going to go, in this direction. Except my fist is a black hole. It's got really, really strong gravitational force when you get close to it. And so you're sort of going to slingshot around. Right? And you're going to be in some sort of orbit around the black hole. And so that's sort of how things fall into black holes. If nothing changes your orbit, then you're just going to orbit around it forever. However, oftentimes there are various processes that make you lose energy. And so your orbit starts to decay, and it starts getting closer and closer in, and that's how you get the sort of spirals that you're talking about. And so Janusz can probably explain this in a much more detailed way.
So as I was mentioning earlier, one of the big problems in accretion disk is how the accretion actually happens. Because if you have some matter with some angular momentum, then it'll have an orbit which there's not necessarily any reason that you'd expect the material to actually fall into the black hole unless it's very close. You think about planets in our solar system; they have orbits, and we're not falling into the sun yet. So like I was saying, the idea with including some effective viscosity in your accretion disk is that you have these gas particles rubbing up against each other, and they lose energy and slowly move in towards the black hole. Once you reach this innermost stable circular orbit, then matter will just flow freely into the black hole because there is no stable orbit that they can have that's circular anymore. But yeah, this picture of having a viscous disk is thorny because, as I said, astrophysical gases are basically inviscid, so there is no molecular viscosity. So this turbulent transport is the idea behind how you get this gas to lose energy and fall towards the black hole. Does that answer your question at all?
Yeah, so we saw this really nice slide about the life cycle of a star. And so what happens after black hole?
Good question. So after a black hole, the black hole will just sort of sit there forever.
And
that's it. So, okay, there are a couple ways. So if the black hole has an accretion disk around it, the accretion disk stuff will add on to the black hole, and it will grow in mass. If there's nothing that it's accreting, there are some theories that eventually black holes will evaporate. This is due to something called Hawking radiation. So Stephen Hawking had this idea that all space, there's even in empty space, there's still some baseline level of energy. And this energy can produce particles that sort of pop in and out of existence. And if this happens close to the event horizon of a black hole, one thing that can happen is one of the particles will fall into the black hole, but the other will escape the black hole. And this will actually carry away some of the energy of the black hole. And this process will take an extremely long time because you have to have just the right conditions for this sort of Hawking radiation to happen. And so we're talking about timescales much longer than the age of the universe. But one theory is that eventually all black holes will just very, very slowly evaporate. So I hope that answers your question.
Over the past couple of hundred years, technology has advanced significantly, enabling a lot of this studies that you've been able to kind of stand on the shoulders of giants. Technology is exponentially evolving right now. Are there any technical advancements or processes that are happening that you've got your eye on that you think might be enable the next big discovery?
Sure, yeah. So I guess we can probably do this as a panel, just the four of us, each say like a particular technological advancement that we're excited about. For me, I'm excited about this project that my advisor is actually trying to get funding for right now, which is called the Deep Synoptic Array 2000. So currently, 2000 refers to the number of radio dishes contained in this array. Currently, the Deep Synoptic Array is an array of 10 dishes, and my advisor's now gotten funding to expand it to 110, and now he wants to build 2,000. So why do you want 2,000? The idea is that right now, you actually have to, remember like I was talking about like taking a giant telescope and punching holes out of it, and those are the telescopes, and you're trying to like reconstruct the entire giant telescope? What if you didn't have to do that reconstruction process, right? It turns out that if you punch out enough holes, if you have enough dishes, you can get a good enough approximation of what the actual image from the one giant telescope would be, that you don't even have to do all these fancy algorithms that people have been developing, and that don't actually produce unique answers, by the way. You don't have to rely on any of that process. You don't have to spend the huge amount of computational power required to process all this data. By the way, the Event Horizon Telescope, you should Google some of the pictures of like all the hard drives they had. They had like an entire room just filled with hard drives, like a warehouse basically. It was like, terabytes upon terabytes of data that they just had to crunch through in many different ways. And what if you could skip all that process, right? What if you could build a radio camera and actually just take the voltages coming out of your telescopes and just produce an image right there? And so that's actually possible. With current technology, you just need enough dishes. And so that's what I'm excited about right now.
So something that I'm really excited about, which is actually happening right now, but I would say it could get even better, is something called integrated field units. So in optical astronomy, there have traditionally sort of been two major ways that you can study things. One is with images. So you take a picture. It's like a camera. You take a picture, and you have a picture. And the picture captures a certain range of wavelengths, right? So a certain range of colors. The other way to do it is to zoom in on a single area and break it down into all of its different wavelengths, like across a huge wavelength range. So that's spectroscopy. So these integrated field units are really interesting because they combine the two. So you have an image, but at every single pixel in the image, you also have a spectrum. So it's like a data cube. You have sort of 3D information about both the position, and also you have all this information encoded in the wavelength of the wavelengths of each pixel. At each pixel, you have information about what's happening at all the different wavelengths. So that's actually a really, really exciting technique. You can use it to study galaxies, hypothetically. If someone hypothetically were to be interested in galaxies, you can study things like, you can take a picture of the galaxy, and normally when we do galaxy spectroscopy, we have to sort of average over the entire galaxy, but not anymore. Because with integrated field units, now we can actually look at individual regions within a galaxy and connect it to sort of the broader environment of the galaxy. And so I think that's something that's really, really cool. I mean, they can be used for all kinds of other things too, but that's what I'm excited about.
I was trying to help with illustration, but I failed.
Okay.
So for me, I have two answers for you. One is kind of similar to Mia's answer, which is in a way an integral field spectrograph, but it's a bit different. So, is it? Yeah.
Sorry.
Yeah. Anyway, so with the CCD or the sensor that we have in our camera, the pixel is actually, don't know any color information at all. It just knows that there's one photon hitting it with the color either from like blue or red. It doesn't care at all. It will register that 1 photon have arrived. There's this new technology called emit, or let's see if I can do it. Microwave kinetic inductance device or something. Is it? Detector, yes. And the promise is that this is, instead of using a semiconductor or like silicon kind of chip, it has this very elaborate superconductor-based material where when 1 photon comes in, it knows exactly when this happens. You don't get that with a sensor that we have right now, with a semiconductor sensor. So with these equipments, you get the time of arrival very, very precisely, and you also get roughly the energy of the photons. So currently, the device with most pixel has about like 1,000 pixels, which is a lot less than a digital camera that we have, that we can have like 12 or 30 million pixels easily. So this is a technology that is being built right now. And actually, I think the first device that is used in astronomy was on that telescope, on my favorite telescope, the Palomar 200-inch telescope. So yeah, this is pretty much being made. Another thing I will say briefly is a concept called thin film optics. And this is super exciting because currently when you want to bend light, you make a huge piece of glass into weird shapes called lenses. And then you hope for the best that it will focus your light into a point. Usually it does that relatively well, but if you are a photographer, you know that good lenses are very, very expensive because it's so hard to polish the surfaces of these glasses to make good precision out of it. There is this new technology using something called liquid crystal, which is kind of similar to what we have in our LCD screen. That's what LCD stands for, liquid crystal display. But in these devices, you can use these crystals to interact with the light in the same way that a piece of glass with different thickness interact with light. And then you can focus light with like a thin sheet of material. So it's really cool. It works quite well. And again, one of the instruments that I work on that telescope also has one of these devices inside, and it's exciting.
So I'm a theorist, so I don't have many telescopes.
You can use a small computer.
I'm in general excited about the advancement of telescopes, but our capabilities for computation and running simulations have advanced incredibly in the last 20 years, both in terms of our computational power, just in terms of the computers we have, and also in the algorithms that we can use to solve the equations of fluid dynamics and plasma dynamics. So that's exciting to me, because it's very hard to actually solve the equations of fluid dynamics fully without simulations. So.
I'm wondering about the wave and particle duality of light and how that relates to how we attribute the capture of light from a black hole, given that, well, we have these two natures of light. Are we only choosing the particle nature of light that gravity is affecting? And what if we were to say that view light as just a wave which gravity shouldn't affect, correct? Then would we say that it's the massive amount of gravity that's bending space and capturing light?
Yeah, so gravity does affect light as a wave. You see this in gravitational lensing, which is, so Dylan mentioned earlier that in the picture of the black hole that was shown by the Event Horizon Telescope, what you're really seeing is light being bent around the telescope, around the black hole. So a black hole is massive enough that, yes, it can effectively capture light. When we think of the wave-particle duality, the easiest way to think about light is as not really a wave, but as a wave packet. So each particle is sort of a localized part of a wave, if that makes sense. So if you have like, you can sort of think of it as like, if you have a photon here, in a wave picture, oh yeah, Dylan will draw a handy diagram. Thank you, Dylan. So yeah, you can think of the particle version as being like a circle around that like area here. Yeah, the area where all the... This is such a... Sorry, I'm doing a really crappy job of explaining this. I hope this kind of makes sense though. So when we talk about the wave part of light, it's not really wave as like a water wave that will go on forever. It's really an individual photon can be thought of as a single packet of waves. Does that kind of make sense? Yeah. Does anyone else want to explain this in a better way?
I don't know if this explains it in a better way, but imagine that you have a lot of waves, sort of like ripples on the surface of a lake. You get all sorts of interesting patterns because sometimes one wave is going to be cresting. It's going to have a high amplitude at one point, and another wave that's sort of colliding into it has a low, like a dip at that point, and the two sort of cancel each other out. And that's like destructive interference. But what if the two waves that were hitting each other both were cresting at the same place? That would be constructive interference, and that would make the wave look bigger, right? So you can imagine having a bunch of waves sort of traveling together. At some points in space, they're destructively interfering, and at some points in space, they're constructively interfering. And the place where they sort of all constructively interfere, I think, is the wave packet. Yeah, and you can think of that as a particle as well, because the wave packet itself is going to be traveling. You can imagine it as all the constructively and destructively interfering waves moving together, and the place where they're constructively interfering is moving, or you can think of it as just like a particle, which is the packet of waves that is moving as well. And I think that makes sense at all.
Yeah, absolutely. I'm just wondering how a black hole is capturing this wave packet. Given that I thought gravity was affecting wave nature.
Yeah, so I guess in a broader sense, this wave-particle duality basically just means that there's two equivalent perspectives. There's two like sort of mathematical formalisms that you can use to describe the same underlying physics, right? So you can think of it as particles being bent around a black hole, or you can think of it as wave packets being bent around a black hole, and they're really just getting at the same like underlying nature, right? The same underlying physics. Waves and particles are really just like our own mathematical ways of writing down what's actually happening out there, right? And the same phenomena happen in both descriptions.
Yeah, I guess one way to say it is that what black hole is affecting is that it bends the actual space. So whatever your light is coming through, whether you think about it as a particle or as a wave, it sees this distortion in space, and it follows it.
Regarding the accretion disk and the temperature in it, you said there's no viscosity, so it can't be viscous dissipation, which causes the temperature rise. So is it through the magnetic fields that it's rising?
The dissipation in a disk can be attributed to a lot of processes, but one of these is essentially viscous dissipation due to a viscosity from the turbulence.
Well, turbulent viscosity, or eddy viscosity or something like that. All right.
What's the best explanation for supermassive black holes existing so early on in the, I guess, evolution of the universe? And I guess, is that any evidence that there was that's a relic from a previous bounce or something like that?
Yeah, so I think the correct answer is that there is no current best explanation, because there are, I don't want to say problems, there are certainly a lot of hurdles that a lot of these theories have to overcome. So one thought is that there are seeds of, one of my professors has like this t-shirt that has this massive flow chart with all of these theories, and I've literally forgotten all of them. But a lot of them involve a lot of mergers really fast. So if you have a bunch of black holes and you can just somehow merge them all really quickly, like in the right environment, maybe it's possible where you have a bunch of seed black holes and they all just happen to merge very early on, then you could get to these supermassive black holes. There are some where there are these primordial black holes that are already like pretty massive, and those happen because hand-wavy old stars are weird. I don't know. There's a cosmologist in the first row who's shaking his head and like judging me. Sorry.
Yeah, so I guess just to give everybody else sort of context for where that question's coming from, we observe these active black holes from very, very early on in the universe's lifetime. And these black holes, in order to be as bright as we see them, have to be extremely massive. And that sort of presents an issue because there is a maximum rate at which a black hole can grow. And the reason why there's a maximum rate is that you have to get lots of material to fall into the black hole, but as that material is falling in, it's going to release energy, and that energy is going to blow out material that's trying to fall in. So there's sort of like a self-regulation process to black hole growth, right? And so it appears that there are black holes that are so massive, so early on in the history of the universe that they couldn't have started from the 10 times the mass of the sun kind of black holes that are thought to form in supernovae. Because if you started with a black hole that small, it would never be able to grow fast enough in the amount of time that is available in the universe's lifetime, up until when we observe it, to become the mass that it is at that time. So there are some potential solutions to that, which is maybe instead of starting out as a stellar mass black hole that's like 10 or 20 or 30 solar masses, maybe it started off as 1,000 solar masses, right? And it turns out that actually the rate that a black hole can grow depends on its mass. And so if you start out by with like a 1,000 solar mass black hole, that sort of solves all your problems. But then the question is, where did that 1,000 solar mass black hole come from? And so people have put out theories that maybe in the very early universe, gas was really, really hot, and it was really hard for it to actually collapse into stars. So maybe things could build up to the point where like 1,000 solar mass clouds didn't quite collapse yet, and all of a sudden you get enough gravity and the whole thing collapses directly into a black hole. That's one theory. Another theory is that there are these primordial black holes left over from really, really early times in the universe's history, which nobody really understands. And when nobody really understands something, that gives you lots of leeway to, come up with things that could possibly have happened, right? And so, the idea is maybe, quantum fluctuations created these black holes, or maybe Luis in the front row knows more about primordial black holes. But that's another possibility as well. And I'm sure there are many other theories too. Yeah.
Let's do 2 last questions.
Hi. Not really sure who to address this question to, but what's going on with the 30-meter telescope?
So there's a wide range of opinions, but we cannot represent Caltech. If you want to talk to us about our personal opinions, we're happy to do that after the panel. But right now we can't discuss. I don't think this is a good forum for discussing our feelings about it.
Well, I was not opinions, but what's going on? How is it progressing legally?
Okay, so a hashtag just the facts version. The 30-meter telescope was due to start construction in July. There have been, over the last 10 years, there have been a series of legal challenges that was eventually brought to the Hawaii Supreme Court, which ruled that the TMT, after some adjustments to their initial environmental impact statement, could begin construction. And so it was due to start in July, but a large group of people have opposed the construction and blocked access on the main road to the construction site.
Thank you.
Yep.
So I guess this goes back to the whole accretion disk and everything. My question would be is, why in general is it a disk and not, say, you know, it's in space and everything, why not a sphere? Why does it want to go to a disk shape? Or, because I'm assuming, like, say, a black hole is approaching a star and you random particle that's in orbit, they would orbit around that, whatever they're going, so it would eventually be like a cloud that's falling in. Why does it eventually go into a two-dimensional disk in the first place?
Yeah, so you can think about the most natural thing to think about if you had a gas cloud that's collapsing to form a star would be for everything to just collapse inward. But in reality, all that material is rotating at least a little bit in some sense. So there's some bulk angular momentum that this collapsing gas cloud has. And if you think about swinging a bucket of water around, there's a centrifugal force which will cause the water to not fall out of the bucket, right? So that force will preferentially support against gravity in one direction. So you'll get a flattening of this disk. With the low-mass black hole binary systems, instead of a collapsing gas cloud, you have material coming from another star. This material will similarly have some angular momentum, and so you'll get the same centrifugal support against gravity. So that's why you have a very flat disk. But you can actually have much thicker disks, depending on how hot the disk is, because if it gets really hot, then it becomes puffy. And you have the pressure force within the disk supports in a different direction, and you get a thicker disk that people argue about whether you have disks or accretion tori, so they could look more like a donut or almost a sphere with the center cut out. So yeah, there's a lot of different geometries you could have. But in many cases, there's just looking at the expected balance between the pressure forces and gravity, you would expect a very thin disk.
Is it possible for it to go and say a cloud or so? Like, is there a situation where that might happen? Has that ever been observed, or is that something that like very, very, very unlikely to ever be observed or ever happen?
Well, so your first question, you mentioned stars having orbits sort of in a sphere, like a random orientations around the black hole. And the difference between the stars and the gas in an accretion disk is that stars are what we call collisionless particles. So if you have, stars are so far apart and so relatively tiny that it's really hard to actually get two stars to collide face on. Like if you just dump a bunch of stars and let gravity run in, I don't know, a simulation, it's actually really, really hard to get any of these stars to significantly affect each other's orbits. And it takes a really long time for them to for every single star to affect every other star. Gas is a little different. So as Janos said, gas can do things like rub up against each other, and it can collide with each other and cause shocks. And this is why gas is able to flatten into a disk, but the stars will not. They'll just take forever to do it. Does that sort of answer your question?
Yeah.
Okay, so back to the gas. Janos can maybe address if there are observational scenarios in which you can get if there's observations
cloud,
about,
cloud falling into a black hole from all directions, not just say going in from, like, say, a disk.
I don't think you'd ever really expect that to happen. I mean, there is a mathematical solution that gets taught in every fluid dynamics course. It's called Bondi accretion, where you just have a fluid flow directly onto a star or a black hole. But that's actually put into a lot of cosmological simulations, I think. But in most realistic cases, you would expect some rotation in a donut or a disk of some sort.
Thank you.
All right, it's past 10. I'm sleepy, and let's all go to bed. Thank you so much for coming, and thank you to the panel, and see you next month.